Welcome to Lecture 33, in which I continue the discussion of fermionic quantum field theories. Recall that in the last lecture, we derived the quantum field theory partition function for a single free Dirac fermion. It's given as equation 33.1 in this slide. Here the gamma e's are the Euclidean version of the Dirac gamma matrices, and the fermions psi and psi bar obey antiperiodic boundary conditions in the time-like direction, such that psi of tau is beta is minus psi of tau is 0, and correspondingly for psi bar. In this lecture, I will tell you how to actually solve this fermionic partition function using very much the same techniques as we did for the real scalar field back in lecture 6. We start by writing the fermionic field as a sum over Fourier components, which I call omega tilde, in this case here. And the main difference with respect to the real scalar field is that because the fermions are antiperiodic, the corresponding fermionic Matsubara frequencies omega tilde have to be given by pi t 2n plus 1, where n is any integer number. Note that the fermionic Matsubara frequencies, unlike the bosonic Matsubara frequencies, which where omega is 2 pi nt, do not contain a zero mode. Similar to the bosonic theories we discussed back in lecture 9, we can also transform the spatial components of the fields psi and psi bar to Fourier space. So we have a corresponding sum over the wave vectors k. V here denotes the associate volume of space. In principle, we would also have to specify the boundary conditions for the fermions in the space-like directions, but if we take the infinite volume limit, these boundary conditions will be unimportant. We can take the boundary conditions to periodic for now in space and antiperiodic in time. So we define a fermionic Euclidean momentum p tilde as omega tilde, the fermionic Matsubara frequency in the time-like direction, and the usual wave vector p in the space-like directions. In this notation then, the Fourier transform of psi to Euclidean momenta k tilde is given by this equation here. And because psi bar involves the Hermitian conjugate of the spinor, this involves a minus sign in the exponent of the Fourier transform. If we plug these expansions back into the action that was given in the first slide of the present lecture, we find that the action is given as 1 over the volume of spacetime squared times the integral over spacetime d tau d3x times the sum over the Matsubara frequencies for the spinor psi bar, as well as the Matsubara frequencies for the spinor psi. The derivative that is appearing in the action then turns into I p tilde from the derivative acting on the psi, and we have the minus sign that's coming in from the Hermitian conjugate in psi bar. We can then proceed to do the integral over spacetime over the only part that depends on x, which is this exponential here. This will give us a delta function that restricts p and k to be the same. And we can use the delta function in turn to do one of the sums, let's say the sum over k, and we will have to replace every k by p. The result is given in this equation here. So we only are left with a single sum over p tilde times this result here that involves psi bar and psi only evaluated at momentum p tilde. And we can use the slash notation to simplify this product of the Euclidean gamma matrix and the fermionic momentum p tilde, such that this becomes I p tilde slash plus m. If we go from usual space to Fourier space, there would be an associated Jacobian in the measure of the path integral that would have to write down. But as was the case with the bosonic theories, that is just an overall constant that we'll ignore. So we find that the fermionic partition function is given as the path integral in Fourier space of psi bar and psi times e to the minus the Euclidean action that we had on the previous slide. Because this is bilinear in the fermionic fields, this is an example of a Gaussian fermionic integral. And as such, we can evaluate it using the rules for multidimensional Grassmann integration that we learned about in lecture 29. In particular, in equation 29.17, we found that the Grassmann integral over Grassmann fields theta I and eta I times the exponential of bilinear that involves a matrix Bij is just given as the determinant of this matrix. So for our case here, we can write the exponential over the sum as a product of the exponential, and then we can do the integral and just get the determinant of the associated matrix that is wedged between the Grassmann fields psi bar and psi. So we find that the partition function up to an overall constant is given as the product of all momenta times the determinant of I p slash tilde plus m. The determinant here is the determinant over spinor space, which is spanned by the Dirac matrices gamma e. Since the partition function is an observable, it is real. And for a real observable, we can replace the determinant by the complex conjugate of the determinant, or we can do the product of these two times the square root, which is the equation that we have here. So we replace the determinant of something that in principle could be complex by a determinant that is manifestly real, which is the square root of the operator times its complex conjugate. Evaluating the product of these two is straightforward. So we get that this is equal to the determinant of the square root of p slash tilde squared plus m squared. And the p slash just denotes the product of the gamma matrix and p. So they can use the Clifford algebra of the gamma matrices to write this as gamma A with the same A, which is nothing else but the Kronecker delta for the Euclidean gamma matrices. So we find that the corresponding determinant is the square root of p tilde squared plus m squared times unity in the dimensions of the Dirac matrices, which in 3 + 1 dimensions is just 4-dimensional. So we have a 4-dimensional unit matrix here. And the determinant of a matrix that has only entries in its diagonal components is straightforward to evaluate. We get that this determinant is equal to p tilde squared plus m squared to the second power. So we find that the partition function for fermions is given as an overall constant times a product over the Euclidean momenta p tilde times p tilde squared plus m squared. So we can write this in terms of a product of the Matsubara frequencies, or the n from -infinity to infinity of the corresponding fermionic Matsubara frequencies squared, and the corresponding product over the usual wave vectors p. We have rewritten the Euclidean fermionic Matsubara, the Euclidean fermionic momenta p tilde as just the component in terms of the Matsubara frequencies and the wave vector p. So that gives rise to this combination EP squared here, which is just the sum, or EP squared is just the sum of the momentum, usual space-like momentum squared plus m squared. Obviously, this bears some similarity to the corresponding result for the scalar partition function, which was given in lecture 9. So back then we found that the fermionic or bosonic, we found that the bosonic partition function was given as a constant times the product of Euclidean bosonic momenta times p squared plus m squared to the power of minus 1/2. And we could write this as a sum over all n times the product of the space-like momenta of omega n squared plus ep squared to the power of minus 1/2. Now back in the lectures 6 and 9, we actually evaluated the bosonic partition function. If we ignore the overall constant c, we found that the bosonic partition function was given as a product over momenta p times the result for the harmonic oscillator evaluated at EP. And if we write this sine hyperbolic in terms of exponentials, we can rewrite this as not as a product over exponentials, but an exponentials of a sum of the individual components here, beta EP over 2 plus the logarithm of 1 minus E minus beta EP, which was given in these earlier lectures. Essentially, we can use exactly the same technique as we did for the bosons. We can use the fermionic harmonic oscillator result that we derived in lecture 30 to derive the corresponding result for the fermionic partition function. So recall that for the bosonic series, the harmonic oscillator partition function was 1 over 2 sine hyperbolic of beta EP over 2. And for the fermionic harmonic oscillator, it was instead cosh of beta EP over 2. The only difference is that for the fermions, we have 4 copies because we had these 4 by 4 matrix that we took the determinant of. So instead of just having a single harmonic oscillator for the fermions, we have 4 copies. That gives us a power 4 for the corresponding partition function of a Dirac fermion. Other than that, we can then re-express the cosh again in terms of exponentials. And if we do so, we get a result that involves the exponent of a sum over momenta p instead of the product of an exponential. And the corresponding terms are beta EP over 2 plus logarithm of 1 plus E minus beta EP. We can use the thermodynamic relation to find the corresponding pressure of a free Dirac fermions in 3+1 dimensions. It's given as this equation 33.17 here. And at this point, we would like to take the infinite volume limit where we send v to 0, and the sum just turns into an integral, such that we find that in the large volume limit, the pressure of a free Dirac fermion is given as 4 times integral over space-like momenta p times this expression here. Again, for reference, let us compare this to the pressure of a free scalar field that we had in equation 10.3, which was given as minus integration over d3p times these terms that are given in this equation here. So you should see that these two results have several things in common. So for instance, the term just after the integral is the same, and the logarithm is similar in form, but there's a plus sign for fermions where there was a minus sign for bosons, and the bosons have an overall minus signs where there was an overall plus for the fermions, and there's a factor 4 because we have essentially a 4-component spinor for the Dirac fermions, whereas here we had a single free scalar field when we were treating the result in lecture 10. Nevertheless, if we focus on the 0 temperature case T0, the logarithms don't contribute, and we only have the 0 temperature contribution in the integrals. From this, we find that the pressure of our Dirac fermion is minus 4 times the pressure of the corresponding scalar field. If we recall the concept of these degrees of freedom and the fact that the Dirac spinor has 4 components, we can say that one fermionic degree of freedom is just 1/4 of a Dirac degree of freedom. So that would mean that a single fermionic degree of freedom has 1/4 of our result for PF. Then a single degree of freedom for a fermion equals or the pressure of a single fermionic degree of freedom equals minus the pressure of a single bosonic degree of freedom. If we then were to consider a theory that had equal number of fermions and bosons, their pressures would just add up, and we would get that every fermionic contribution for the pressure cancels exactly one bosonic contribution to the pressure, and the resulting total pressure for such a system would be exactly zero. Since the zero temperature pressure is the same as the cosmological constant, we find that in a theory that has equal numbers of fermions and bosons, the corresponding zero temperature pressure, or the cosmological constant, is just vanishing. This is a key result in supersymmetry, where I just note that supersymmetry is a hypothetical symmetry between fermions and bosons, and because it is a symmetry between fermions and bosons, it requires equal numbers of fermions and bosons. So in a supersymmetric theory, one generically gets that the cosmological constant is vanishing because of this same construction. However, as we've just seen, a result that has vanishing total pressure just relies on the fact that you have equal numbers on fermions and bosons and does not need supersymmetry. And this concludes the present lecture.